Hello, my name is Matt Holliday and welcome back to my Go class again. So in this segment I want to talk about some basic things in Go that we've already seen. I just want to sort of circle around and go into them a little more detail. So things like control statements, packages, declarations, and operators. All right, it's stuff we've already seen. I just want to explain them one more time. Okay, so the first control structure is, of course, we've seen this. It's an if statement. But there's a couple things I want to point out about if statements and control structures in general. So the first is that in Go, if braces are allowed, braces are required. Okay, so the form you see here, this is not a choice. You can't choose not to have the braces. They have to be there even if you only have one statement inside the if part. And the braces have to be laid out in this style, which is sometimes known as 1TBS, the one true brace style, which is enforced by the compiler. The other thing I want to note is, and we've seen this before, it's possible to have a short declaration after the if, right? So we declare a variable for the if statement by running the function, and then the actual comparison, how we choose whether or not to do the if statement, comes after the semicolon where we have the condition. Okay, and we'll see other control structures that allow us to have a short declaration as the first thing. So for loops, we've also seen those. Now, the one I'm showing here, I don't think I've shown yet. This is sort of the primordial for loop going back to C. We have a variable that we're going to increment, an integer. It'll increment typically from 0 up. Okay, and so it has three parts separated by semicolons. We have the initialization part. In this case, it's a short declaration. We have the test part, I less than 10. That's where we decide whether or not we're going to iterate again. And then we have a third piece, which is the post-iteration increment, where we change the loop variable. Because if we didn't do that, the loop would never stop. You know, I would start as 0 and it would always be less than 10 and we just keep going round and round. Now, sometimes that little piece will get moved inside the loop for some reason. Maybe there's a more complicated decision about how to increment. And when I do that, typically I'll put a comment, an inline comment there to show that I've deliberately moved that into the loop. But all three parts of that are optional. I don't have to initialize, and it doesn't have to be an integer. There are some other cases where I can create variables of other types, as long as it makes sense. What I'm doing to check the variable and change the variable makes sense. So in this case, it just goes up from 0. And again, it's very typical for these things when we count from 0. I want to do 10 times. So I start at 0 and I check that I'm less than 10, okay, which means 0 up to 9, which is a total of 10 iterations, right? And when the loop variable becomes 10, it fails the test and we stop iterating. Now, Go only has one type of loop, the for loop. There's no while loop, there's no do while loop, there's no repeat until loop or whatever. So there'll be another form of doing logic where I test at the end, and I'll show that. We've also seen the range operator. It's much more common to create a loop where the iteration is a little more implicit in the sense that I don't increment a variable. I use the range operator to work its way through a structure like a slice or a map. In the first case here, I'm showing a slice. And the range operator is going to give me 1 or 2 values. It's another one of these cases where I can have 1 or 2 values returned from some operator. In the first case, I is an index. It's an index of an item in the slice, and it's going to start at 0 and go 0, 1, 2, 3 for however long the slice is. Okay. In the second case, I get I and V, where I is the index and V is the value that's at the index. And the one important detail is it gets copied. So whatever this is over here, let's suppose it's an array, I'm going to copy a value out of the array and put it into the variable V as part of this for loop. Which is fine if it's an integer, that's small. It's not fine if my array is an array of 4K blocks and I copy 4K every time I go through the loop. I might not want to do that. It might be better to use the first form and just use subscription notation and be more efficient. In the case of a map, it's very similar, except the first variable is the key, because a map is not a sequence, it's sparse. And so either we get one variable, which is the key, so I can iterate over the keys by themselves, or I can iterate over the keys and the variables in the map. And again, whatever's in the map gets copied into V for that key. And in both of these cases, the loop runs as long as there are things in the map to loop over, or the slice. If the slicer map is empty or nil, the loop doesn't do anything at all. I also want to point out a particularly important detail about maps. Maps in Go have no order. Okay, if you go to C++, the original map was actually based on a tree structure, and it had an implied order. The keys were always ordered essentially alphabetically. In Go, there's no order in a map. It's based on a hash table. And so different times that you iterate through the map, you may get a different order of keys. In fact, you should. Certainly if you run the program again, and sometimes even within the program, if you loop through the map in a couple different places, assuming the map has more than 1 or 2 keys in it, you're going to see the keys in a random order. If you need to go through a map in like an alphabetical order, then what you do is you extract the keys, sort them, and then you run through a list of sorted keys and go back to the map and get the values based on the key. It takes a little bit more work, but there you are. Because if you go back to C++, in those original maps that were ordered, you were always paying a tax to have them be ordered. And if you didn't need the order, you were still paying a tax, a runtime tax, to keep them in order. And what Go does is, here's an unordered map, and if you want order, well then you can impose your own order on it afterwards and make it clear that you're doing that. So here's another form of for loop. In this case, well, there's nothing there but the for. And that's perfectly okay. I can leave out everything and just start what is effectively an infinite loop. There are even a few cases where a program might want to have an infinite loop. You know, you start just doing something and you just keep doing it until the program stops. But in this case, I'm doing it because I want to put the logic in the program later in the loop. I need to do the equivalent of a do-while loop, where I do the first iteration and then I check the condition and go back. Well, there's no do-while loop in Go, so it's a for loop with my own explicit check and a break statement, where the function of the break statement is to stop the loop. Okay, and there's 2 of these. There's a break statement, which I've shown, and then there's another statement called continue, and the function of continue is to make the next iteration start early. Now, on this slide, I've got a common mistake, and I've also got a pattern. You may see a few slides where I invert the colors. It's a black top with red letters. Scary. Okay, it's a common mistake because I make it commonly. Maybe you don't, but I do. And that is, I want the value out of the slice. I don't want the index. But if I just write one variable, the variable is going to be the index. And if I want the value without the index, I have to write it in this form. I have to use the underscore, and the underscore is just a placeholder. It says there's a variable here that doesn't have a name and we don't care what it is. So I put underscore comma v. V gets the values, the underscore ignores the indexes, and I can't do it any other way, because if I didn't have the underscore, then the v would be understood to be the index values, and I couldn't get the values themselves, just the indexes. There's one more bit of complexity, and that is I sometimes have nested loops, and I need to do my break or continue in the inner loop, but have it affect the outer loop. Now, what I'm doing here, just to make this more comprehensible, my model here, and this came out of a real program, I have some list of keys, and for that list of keys, I have some other list of data, and I want to see whether the key here is in this second list. And if it is, well, that's fine, I found it, and move on, and if it's not, I want to report an error. So my outer loop is looping over this part, and my inner loop is looping over this part. And as soon as I find the key in the inner loop, I'm done. I don't need to keep going all the way down this slice, which could be big, because I've already found it. So I want to do a continue. I want to go back and get the next key and start this process over. So I need to do a continue from the inner loop, but what I'm actually continuing is the outer loop. And I've done that by giving the outer loop a label. Now, the word outer here is just an identifier. I picked it. Convenient for me to use outer. It makes it pretty clear because I'm saying continue outer, and I gave the outer loop the name outer. But it's a label. I made it up. It's some name with a colon. And it's just a label. It's a target for that continue to go to. Right? So, and of course, if this inner loop does not continue, so I go through this inner loop, I look at this next key here, and I go through the whole thing and I don't find it, then I drop out of the inner loop down to this piece where I say, hey, I'm going to report an error. Okay, so if and for we saw already. The third thing I want to bring up is a switch statement. Now, technically speaking, the switch statement is unnecessary. It's syntactic sugar for a whole bunch of if-then statements, or if you like, if-else statements. Okay, anything I do with switch could have been done with ifs, but it's clearer sometimes to write it as a switch, and it's just more understandable. It's just more readable. Okay, there's two kinds of switch. The first one I show here is the one that's more common in the sense that the cases have discrete values. So again, I have a short declaration, which is optional, and then I have the thing that I'm switching on. I'm going to look at this variable a, and I'm going to find a case that has a value that matches. And each case has some number of values, discrete values listed. Now, they're not supposed to overlap. I can't have the value 2 in two cases. Okay, that's rule number 1. Rule number 2 is it's perfectly okay to have a case that doesn't have any statement. So it's a no-op. Although usually I'll put a comment there. I'll actually put a comment to make it clear that I intended not to have an executable statement. The third thing is missing. If you look at this slide and you're familiar with, say, C or Java, you're going to say, hey, wait a minute, where's the break statement? And Go switches are different. The cases break automatically. There's no need to put a break at the end of each case to keep one case from falling through to the next. In fact, if you want fall through, which is rare, there's an explicit keyword to make fall through happen, which I generally don't see in real programs because normally you don't want that. Right? And the more common mistake, it's a very common mistake in languages like C and Java, to miss a break and accidentally fall through to another case and have your program do weird things and you wonder why it's doing those weird things, and finally you realize you're missing the break. Now, there's one more detail, and that is, generally speaking, case statements go from top to bottom, right, in terms of how they evaluate things. The default is always last. Now, it's always, no matter where, you could put the default anywhere in the switch statement. It will be evaluated last. I write it last because that helps people understand that's the way in which it's going to be executed. We're going to look at the other cases, and if none of them match, then we're going to look at default. So I always put it at the end just because it's clearer that way. But the default will always be looked at last no matter where you put it. Okay, and then there's one more thing about Go. There are a couple languages out there where the compiler says, hey, I'm looking at some enumerated type, and you haven't covered all the cases exhaustively. And Go doesn't do that. First of all, Go doesn't really have enumerated types. There's something that looks like an enumerated type that I'll talk about later. But Go does not attempt to tell you, hey, there's a possible case that you missed. It's up to you to make sure you've covered all the cases, usually by just making sure you have a default. There's another form, and the other form is called switch on true, and just like a for loop with nothing, it's a switch statement with nothing. There's nothing there after the switch but the curly brace. And the way it works is that instead of having cases with discrete values, the cases have tests, logical tests like you'd find in an if statement. And literally, it's like a bunch of if statements, one after the other, right? We'll start with the first one. Is it less than 2 or equal to 2? Fine. Is it less than or equal to 8? Okay. Otherwise, we'll take the default. So it's a slightly different version of switch. Again, it can be more convenient and more clear to write it this way than to write a bunch of if-then-else statements. But it has the same purpose. Now, there's a third form of switch I'm not going to show right now, where instead of switching on values, we're going to switch on types. And I don't want to talk about that until we get to the part on reflection, where we do some fancy things with types in Go. That's going to come later. It's kind of an advanced topic. Okay, so packages, we've again looked at those. We've already seen those in programs. All of our short programs had package main, and there was one example program where I had a package hello. Okay, in Go, everything lives in a package. So every Go source file is going to start with a package declaration. It's going to identify this file as being part of some package, and so everything in Go lives inside some package. There's nothing that's sort of global in the sense that it floats outside of all packages. So that really means there's two kinds of scope. There's package scope, which means outside of a function, and then there's function scope, which means it's inside of a function. And when we talk about declarations, right, the one rule was the short declaration operator could only be used inside of a function. And the reason for that is if we look at other declarations in a package, they all start with a keyword. The first thing is going to be a keyword, and it's just easier to parse. And that's why it was done this way. Okay, so there's a bunch of things we can declare in a program, and we can declare them all at package scope. We can create types and variables at package scope, but we can also create them inside functions. We'll see that later. Okay, so why do we have packages? Well, the main purpose of packages is to break the program down into parts that we can think about independently. Okay, this is either called encapsulation, or there's an earlier term, information hiding, means the same thing. And that means typically in a package, there are things we want to allow other people to use, and then there are things we want to keep private, right? And so the question comes back, what identifiers are exported? Because the exported identifiers are the ones that another package can refer to. And in Go, the rule is very simple. If it starts with a capital letter, it's exported. And that's actually easier than some other languages. There are some older languages where you had to have two files, the file of the things that get exported, and then the file of the actual function bodies. Ada worked that way, Modula 2 worked that way. It's cumbersome. So the rule in Go is you have this one file, and if it's capitalized, it's exported. And if it's not, then it's private to the package. Now, a package can have more than one file. There can be 3 files of Go code in secret package. All 3 files see everything in the package. Okay, so anything in one package, anything in one file is visible to the other files, but everything in the package is only visible inside the package unless it's exported by being a capital letter. And we've seen this implicitly because every time we use these functions like from funct, you'll notice that functions like printline, well, they all started with a capital letter. And if you wondered why that was, well, that's because those are the only things we can use. Right? There are things inside the funct package that start with a lowercase letter. They're private to the funct package. They're part of how it makes its stuff work. And the idea is not to expose all that, just to expose the API that we're actually supposed to use. Okay, so imports. Every file in a package must import the things it needs. So again, if secrets is a package with 3 files, each file may have a different import statement, because I have to import everything I need in that file and nothing that I don't. So for example, let's suppose part of my package needs sort. Well, only the file that uses sort is going to import sort. And if I don't use it in a particular file, then it's a compile error. You can't import something you don't actually use in the file. Okay, so I don't have, import is not like on the basis of the whole package. Every file has its own import and it has just what it needs for that file. There's another rule. And this is a restrictive rule in Go. There's good reasons for it. Some people, again, don't like it. Packages cannot have what are called cyclic dependencies. And what I mean by that is, if A uses B, then B cannot use A. So if we think about how packages get used, right, we have little arrows, right? So maybe main using A, and A uses B, and B uses C. Well, this is fine until somebody creates an arrow from C back to A. All right, so if we didn't have that, the graph would be a tree. A graph with no cycles is a tree in algorithm terms, and that's what we need for dependencies in Go. It's a tree-structured dependency list. All right, cycles like this are a problem because it's like chicken and egg, right? Which one goes first? Well, A needs B, B needs C, but C needs A. Where do you start? You just go around and round and round. Okay, and the way that Go wants to compile, in order to be able to compile very quickly, it's just not possible to also allow cyclic dependencies. That's reason number 1. Okay, there's another reason, and it has to do with initialization. Now, we may have things at package scope. For example, we have a couple of variables. Those variables need to be initialized at the beginning of the program before main starts, right? So there are some things that happen before main starts. Variables get set up. And it's also possible to have a func called init in your package with a lowercase I. It's private. How does it get called? It gets called implicitly. The init function in your package gets called when your package gets started up in some order based on how the packages relate to each other. Well, again, if there were cyclic dependencies, we would not know how to order them. You know, A needs B, B needs C, but C needs A, so which one goes first? We don't know. Okay, so we always have a tree-structured dependency, so it's very clear how to initialize the data in the package, even if you don't have an init function. Now, the init function is useful. It's also controversial. There's some smart people who say you shouldn't use them. It's not good style to have these little packages of things initialized, hidden away inside a package where it can't be seen. But you will see it in Go. For example, if you're using SQL in Go, then you're going to see that you need to pull in a driver for the database you're using, like MySQL or Postgres. And when you do that, that driver is going to have some init code to set itself up. You might also use this if you were doing plugins in Go. I haven't done plugins with Go. I've done them in other languages. And it's a plugin is a little piece of code that you pull in at runtime after main starts. And it's very useful for that little piece of code to be able to initialize itself before you start using the functions of it. So inits have their uses, and I don't think there's reasons to say you shouldn't go overboard with them. It's just like anything else. They can be abused and possibly make your program harder to understand, but there are also cases where it can make your program simpler. So I've talked a little bit about packages. I want to talk one non-technical thing. Not about packages in Go, but packages as a concept. Again, I said they're about information hiding. So what makes a good package? Okay, people have been thinking about this now for, I don't know, at least 50 years. So there's a professor named Osterhout at Stanford. He wrote a book. It's called Philosophy of Software Design. And I don't really like the title. I think it's off-putting, but it's a great book. It's based on his experience of trying to teach a software design course to undergraduates, which most universities don't even do. All right, and one of the things he addresses is, what makes a good package? And the idea is that a good package encapsulates deep, complex functionality behind a simple API. Okay. Now, the example I want to offer is kind of my best example of any API, and that's the Unix file API. I've shown it here sort of how it is in Go. And there may be a couple more functions than I've shown here, but these are the basic functions. And if you think about what files actually do in real life, it's very, very complicated because the operating system has its own scheme for buffering. It has device drivers. You have file systems now that are very complicated, like ext4 and other journaling file systems. Then you have the disk stuff, and the disks have gotten more complicated. There's different kinds of disks, there are different interfaces, and maybe the disk has its own buffer inside of it, or maybe the disk is even visible across the network using a protocol like iSCSI. So when you think about what actually happens when you say, I'm going to write some data to a file and then save the file, right? In the real world, underneath all those layers, it's pretty complicated. But here's this nice, clean, simple API, and it's a good API. It's been battle tested for, 50 years now. Okay, and it stood the test of time. So it's a great example of how to think about, how do I package something? And again, what I really want to do in a package is hide some complication, build some deep functionality, but build it behind a shallow or narrow, simple API that's easy to use. And that's sort of how we make good packages. So next up are declarations. We've seen a bunch of declarations. I want to talk about a couple of details. So first off, there's a bunch of things that can be declared. We can declare constants and types and variables and so on. Now, variables can be declared two ways. There's a var keyword, and then there's our funny little short declaration operator. Okay, and they can be declared in a package or in a function, except the short declaration operator can only be used in a function. Okay. If we use the var keyword, we must give either a type or a value where the value can tell us what the type is. In other words, the compiler must be able to infer the type from the value. So in this first case, var a int, that's straightforward. Okay, what value will it start with? Well, it will start with 0 because that's the default value for int. And every variable, again, is initialized somehow at the point of declaration. Either you give it an explicit value in the code, or the compiler will give it a default value based on the type. Okay. The third one, var c equals 1, it's an int. So we have the value, not the type, but the type is known because the default for 1 is going to be to treat it as an int, so c will be an int. So what about b? Well, b is kind of overspecified. We've given it a type and a value. And we wouldn't often do that unless it had a different type. So I'm going to show you something. We really haven't talked about unsigned integers. Well, what happens if I needed var b to be a uint and be equal to 1? Okay, well, so the value of 1 by default would infer as an int, a signed integer, but I want it explicitly to be an unsigned integer. So now I need to give it the type and the value. So you will see this occasionally. Okay, and the fourth one is clear. It's a 1.0, therefore it's a floating point constant, therefore d is a floating point number. Now, if I have individual declarations, I'll do this. I don't like putting lots of vars in a row, and thankfully, Go has this notion of a declaration block. We've seen this with import. We can put import parenthesis and then a bunch of things in close parenthesis. We can do it with var. We can put the var keyword and then a block in parentheses where I give it names and types, for example. And I don't have to repeat var, which is fine. And oh, by the way, when this is formatted, it will actually format and look like this. It will line things up in a neat way that makes it more readable when you're looking at a block of declarations. Okay, so that brings us to our friend, the short declaration operator. And when I look at this, I think, oh, that's the Pascal assignment operator. And it sort of is a short declaration operator, and it sort of is an assignment operator. It has some rules. The first couple rules are pretty straightforward. It has to be used in a function. And also, if I want to declare a variable at the beginning of a control structure like if, it's the only way to do it. I can't write if var v something. I have to write if the variable short declaration operator and then some value. Okay, that's great. The third rule, you're going to start wondering what? And it has to have at least one new variable. And so I'm going to dive into that just a little bit. Because again, the short declaration operator is kind of having a double life. It's also partly an assignment operator. So if I look at the first thing here, and I apologize, the semicolons are a typo, right? I've declared the variable error. It gets its type and value by calling this function. Great. The next line is a mistake because effectively I've redeclared error and I can't do that in the same scope. So that's wrong. But the third line is perfectly okay because I'm declaring x, it's a new variable, and then I'm assigning to error, I'm not redeclaring it. This error is the same as that error, assuming this is all part of one little function. Okay, so that's why I say it has to have at least one new variable. The new variable is declared, the other variables are reused and assigned. Okay, great so far as we go, except for one little thing, rule 4. And rule 4 says, well, that only applies to a variable that was declared in the same scope. Okay, and that means in the literally the exact same scope, not including an outer scope. Right? Now we're accustomed to thinking about programs, you know, where a program is like one of these Russian Matryoshka dolls, right? I have blocks inside of blocks. I can declare a variable b out here and I can declare a variable at an inner block. And the variable b at the inner block shadows the outer b. So inside this inner block, the b that I see is the inner b. And outside of that, I see the other b, the first b. Okay? That's pretty straightforward when we just do normal variable declarations. What makes it weird in Go is sometimes that's hidden. We see the short declaration operator and it's partly assignment, it's partly declaration, and it's not obvious when we look at the code sometimes that we're shadowing a variable in this sense when we are. Here's an example of shadowing a variable from outer scope. Now, this example is nice because the compiler will tell you you're wrong. Okay. Now the code in here is complete junk. I would never write this code. Like, technically speaking, print line returns an error. We don't check it. Why? It doesn't mean anything. All right. So this code is very much made up, but this error here is being declared in the scope of func main. Great. But there's another scope in here, and that's the scope of the if statement. The if statement's its own block. This declaration here, the short declaration, is local to the if statement and its else clause. Okay? That's very important. And that's true of all these control structures. If they start with a short declaration, the short declaration is local to the control structure in that block. So they're not actually at the same scope. They're not the same variable. This is not a case of assigning to an existing variable error. This is actually a declaration of a new error in a new scope. Now, why does the compiler catch this? Because this one never got used. You're not allowed to declare a variable that you don't use. And so the compiler says, hey, you declared it, you didn't use it, you didn't read to it, write to it, so it's wrong. And that's straightforward, that's nice. We find that error pretty quickly. The next slide has an error that the compiler cannot find. And the reason for that is, and notice here, it doesn't matter, this error out here, the outer error, we didn't use a short declaration. It doesn't matter, it got declared, however. It's being referenced down here at the bottom, which is why the compiler will not complain. Error was declared at the top, it's used at the bottom, the compiler says the variable was used, but it's not being used the way we thought it was. Because inside here we have this for loop, and in the for loop we have the notion of we're going to call the read function, look at the error, break out of the loop, and the mental model that we had writing the code was, well, we're going to report the error that came back from read. Except we're not. Because this, the error in here that's assigned to from the read call, it's declared and assigned to from the read call, it's checked to do the break from the loop, goes away once we leave the loop. It's local to the loop. And the error that we're returning is always nil because we declared it and never assigned to it up here at the top. So no matter what happens to this function, whether it has an error or not, we're going to report that no error actually happened. And that's a logical bug. And the compiler's not going to complain about this, right? And this is not a unique Go thing. I mean, if we did this with vars, right, there are plenty of other languages would let us make this mistake by using some sort of var declaration of the same variable with the same name, all right? And the reason it's more interesting in Go is just because the fact that the short declaration operator is this little thing that sort of looks like declaration and assignment just makes it harder to see it. Okay, so I've just talked about declarations. I want to talk about types because Go is a statically typed language. And types are really about what's compatible in the sense of what can be assigned to what. Can I assign B to A? Is that legal or not? Does that make sense? And we use types to make sure we only do assignments that make sense. Now, what does the same type mean? And so there's a couple different ways of thinking about that. There's structural typing and name typing. For the most part, we're going to look at structural typing. And that's the case of the type has the same structure or behavior. Okay, this can be called duck typing in the sense that if it looks like a duck and quacks like a duck, it's a duck. So here's an example where we have a couple of arrays of 3 integers. Are they compatible? Well, yes, because arrays are typed based on their size and their base type int. They're the same size, they're the same base type, we can assign one to the other. So the B to A assignment is legal. The C to A assignment is not because C is an array of 4 ints and the size is part of the type and 4 and 3 are not the same, so it's not the same type. Great. So there's a bunch of rules around this. And here they are, right? I've given the example of the array. We could say slices, do they have the same underlying type? Or a better example is functions. Do we have the same type of parameters in the same order and the same quantity of parameters? Okay, if they match, they match. So when do we use named typing? We use named typing when we explicitly introduce a type with the type keyword. So here's an example. We've created type x int. So x has the same structure and behavior as int. It's the same size, we can put the same kind of numbers into it, but we've given it a different name, and we did that deliberately for some reason, and so logically it's a different type than int. So what happens then is, here's an example, var a has type x, we declared it that way, and var b has type int, because 12 defaults to an int in terms of initializing b. Can we assign b to a? And the answer is no. They are not compatible because they're not the same type. Now they have the same underlying type, they're both ints, so they have the same structure and behavior, but because we gave x a particular name, a different name, it's a different type. Now there's a couple things we can do, right? Can I assign 12 to a? Yes, because numeric literals get special treatment. They're sort of untyped, other than, we have an integer versus a floating point number. And I can assign b to a if I convert it. So that's what's going on here at the last thing. I'm doing an explicit type conversion. So you know, in this case, it's kind of trivial because, again, their underlying types were the same. It gets more interesting when we talk about unsigned integers and integers of different sizes, or I need to assign a float to an int, which means I got to truncate it. In certain languages, there are a bunch of complicated rules about how this stuff happens automatically. Some of those rules are defined, and then there's a few things it's like, oh, that's undefined, and who knows what happens when you do that. And when you read the program, it's very difficult to remember all those rules and apply them when looking at any given statement. Okay, which is why it's, you know, you get a language like C and you can write some code and it looks nice, but the rules may not be what you think they are. The compiler may do something different and your numbers may end up getting funny. Okay, I don't really want to get into bitwise operators and low-level code, but things happen. And what's good about Go is we make that explicit. If you want to convert an X to an int, or, you know, if you want to convert a 32-bit int to an 8-bit int, or you want to convert an unsigned int to a signed int, or something like that, you're required to go ahead and put that in the code. Here's a type conversion. It's very explicit. I know what it's going to do, the compiler knows what it's going to do, and somebody else coming and reading it a year from now will know what it's going to do. So it's name typing in the case of user-declared types. Okay? In most other cases, it's structural typing. I want to mention numerical literals real quick because I said they get treated special. A general number like 12, I mean, it defaults to an int, but it's compatible with anything that's numeric. I can put a 12 into an int, I can put a 12 into an unsigned int, I can put a 12 into a floating point number. It'll get interpreted correctly. And then there's some other numeric literals that are very specific. You know, if I put a decimal point in them, I'm saying it's a floating point number. If I put an I in there, I'm saying it has an imaginary part. It's a complex number. I don't want to talk about complex numbers. We're not going to do scientific programming, so I don't really want to get into that. All right. And the other thing I'll mention is all of this stuff involving numeric literals and numeric constants, Go does a very good job of keeping lots of precision at compile time. Typically 256 bits or more, which is way more precision than any variable you'll ever have in a running program. So, you know, it's pretty good at that. Okay, so for this last piece, I want to talk about the operators in Go. There's not much to say. There are not a lot of operators. Okay, and they break down into some simple groups. I have arithmetic operators on numbers, and one of them is overloaded. There's only one really overloaded operator in Go, the plus sign, which obviously it's for adding numbers. It's for concatenating strings. Comparison, they only operate on things that support order like numbers and strings. And the Boolean operators only operate on Boolean types. So again, you know, there are some languages, there's a bunch of languages, where 0 gets treated like false and 1 gets treated like true. So we have this notion of truthy or falsy, and Go doesn't do that. Numbers and Booleans are absolutely separate, and they're not really convertible. If I need to make a Boolean from a numeric expression, I need to use a comparison operator and say, is A equal to 0? Okay, that's fine, that's true. That expression is true, and then I can use that logically however I want to. Okay? Bitwise operators, I'm not going to mention right now. We'll come back and circle around bitwise operators and small integers and stuff like that. That's kind of low-level programming, and most people don't need to do that either. And then there's some shortcut operators where they just combine the equals. And again, we said, you know, plus equals is the same thing as s is equal to s plus something. Right, if I do s plus equal to something. So it's just it's a shorthand, it's convenient. If I have a complicated expression, then maybe I can save some time by not writing it a second time. There are some languages where we have like 10 levels of precedence. And what I mean by precedence is, if I have an expression like 3 times 4 plus 5, what's that mean? Well, of course, we want it to mean what it meant in grade school, right? That first you do the multiplication and then you do the addition. And that's what we're saying here. The operators like multiplication come first, and then operators like addition, and then we get to comparison operators, and then below that are logical operators. And the logical operators actually and in some senses like multiplication, and or is sort of in some sense like addition. So they fall out also. And it makes it easy to write things like, you know, is A 0 or is B C? and put that into an if statement and not put a lot of parentheses around it. If your expression is more complicated than this, then do put parentheses around it, right? Again, if there's any confusion, put the parentheses there because you'll know what it means, the compiler will know what it means, and another developer looking at it a year from now will know what it means. Okay, so that sort of wraps up this little segment. I wanted to go back over some basic stuff in Go. It's stuff that we've mostly shown in example programs bit by bit, and I just wanted to kind of solidify that. I'm going to have one more little segment on I/O, formatted and file I/O, and that'll sort of wrap up what I used to have as my first big lesson on the basics of Go, and then we'll move on to some more complicated stuff.